Hello everyone, my name is Arthur and I'm here to present to you our work called Self-Organized Direction-Aware Data Partitioning for Type 2 Fuzzy Time Series Prediction. Along with me are Professor Petronio, Professor Federico, Professor Christian, and Professor Eduardo. It's possible to find challenging behaviors and patterns within certain time series data, making it difficult to analyze and forecast. This scenario has motivated in recent years the development of new forecasting methods, combining performance and low computational costs. One of these methods is fuzzy time series prediction, which is based on type 1 fuzzy logic and has been used to forecast economic series, environmental, traffic flow, among others. One great problem of FTS prediction is how to properly deal with the uncertainty associated to the time series being analyzed, which comes from many sources and is independent of what kind of fuzzy logic or methodology is used to handle it. FTS prediction models design can also be another source of uncertainty. Several hyperparameters must be optimally defined in order to build an accurate forecasting model, including the number of fuzzy sets, the partitioning methodology, and the type of membership function. All these uncertainties within the time series and about model creation introduce uncertainty in the model itself. Thus, FTS recent researches address different issues to improve the forecasting accuracy, including interval partitioning, number of variables, order, and prediction period. One of the critical parameters of fuzzy time series is the number of membership functions, an issue that has been a research topic over the years and is addressed using different techniques. But although the increasing research and interest in the field is recent, there is still much to be explored. Thus, this research proposes a univariate, non-parametric Type 2 fuzzy time series model, capable of taking advantage of the best treatment of uncertainties that Type 2 fuzzy logic presents to build forecasting models. The forecasting model also takes advantage of the self-organized direction-aware data partitioning algorithm, also called SODA, a non-parametric partitioning method with high capability of adapting to multiple types of data. The model was called SODA T2FTS. Now let's talk about SODA. Traditional clustering techniques often require the user to define certain parameters and make assumptions in advance. Thus, data-driven models have been targeted by recent research in an effort to make machine learning more autonomous and less dependent to human interference. SODA is then an autonomous data partitioning algorithm, which is conducted based on the empirical observation of the data alone, without the need for any prior knowledge or definitions. But there is one optional parameter named grid size that can be chosen that decides the granularity of the clustering results. Okay, now let's see how SODA T2FTS works. As you can see in figure 2, SODA T2FTS receives as input the time series data, and then all the steps necessary for training and testing the model are performed in order to obtain error metrics and forecasting results. Let's begin by talking about the training procedure, which is done to learn the temporal patterns of the time series training data, thus building the model that will be used in the forecasting phase. In the beginning, we define the universe of this course using the training data. Assume that the time series is represented by y of t, and the universe of this course is denoted by this equation, where minimum of y of t and maximum of y of t are the minimum and maximum values of the historical time series dataset. Here, f1 and f2 are factors chosen in order to expand the universe of this course, covering variations and noise in the data. After that, SODA is used to define the number of membership functions of the UOD given the data from the time series training dataset, which corresponds to the number of membership functions in the model. Figure 4 shows an example of UOD partitioning using SODA output. Data was inserted into SODA, which was able to identify and split the data into 9 data clouds. Thus, the UOD was partitioned in 9 evenly distributed triangular fuzzy sets. Then we move to the fuzzification part. Each sample from the training dataset is inserted into the model, and the membership values are calculated for all the fuzzy sets in the fuzzification procedure. After that, we move to the rules extraction part. As a time series is a sequence of samples, the relationship between one sample and the next can be analyzed and identified as a fuzzy rule, which also represents the temporal patterns between sequential samples. It's better to understand this part with an example. So let's look at table 1, okay? We have the first sample on December 2nd of 2009. So this sample of the time series is fuzzified as the fuzzy sets A3 and A4. The next sample is December 3rd of 2009 and it's fuzzified also as A3 and A4. Therefore, we can extract the following rules or relationships. If A3, then A3. If A3, then A4. If A4, then A3. If A4, then A4. Observe that for a pair of samples or for two consequent samples, we can extract 4 rules or 4 relationships. Okay, so we do this for all samples in the time series training data, and we extract all the rules for all the samples for all pair of samples in the time series training data, and then we have our fuzzy model, our learned fuzzy model in the end. Then we move to the forecasting procedure. The forecasting procedure takes as input a sample from the time series test data, and the output is generated using the model learned in the training procedure. For a given sample from the time series test data, we calculate the degrees of membership for both lower and upper membership functions for each fuzzy set. The rule matching procedure consists in finding the rules that are activated by each of the fuzzified samples and their respective rules. Aggregation is then performed, which is the process that aims to generate a single type 2 fuzzy set from the rule output fuzzy sets. To complete the forecasting process, a final crisp output value must be obtained for each test value. The aggregated type 2 fuzzy set is first reduced to an interval type 1 fuzzy set using the EASK algorithm, and then, after centroid defuzzification, crisp values are generated. Now I will present our results. The TIEX dataset was chosen to assess the proposed model. The TIEX is a non-stationary time series usually used in forecasting literature composed of 5,200 instances. When evaluating a time series forecasting model, we must take into account that there is a relationship between the observations, which means that they are time-dependent, so cannot be randomly divided into groups. Thus, we must split data respecting the temporal order in which values were observed to provide statistically robust model evaluation and best simulate real-life scenarios. In this work, a sliding window methodology was applied, using a window size of 1,000 instances that was shifted by 200 instances along the time series data. The data for each window were divided into 2 sets, the training set, which contained 80% of the data, and the test set with the remaining 20% of the data. Considering the TIEX with 5,200 instances, the sliding window methodology generated 22 experiments windows, and for each window, training and testing is performed out of sample and then error metrics are calculated. As our first results, we wanted to see the grid size effect in UOD partitioning. We wanted to see how the grid size would affect how so the partitions the same amount of data. So look at table 2 for example. We can see that considering the same data, the higher the grid size, more focal points are identified, therefore more partitions are generated for the same input data. Let's consider the first window for example. For a grid size of 4, Soda partitioned the first window into 11 partitions, and for a grid size of 10, Soda partitioned it into 49 partitions. So we can see that as the grid size increases, Soda allows itself to partition the same amount of data into more partitions. It's also important to note that increasing the number of partitions of the universe of this course translates into a higher number of membership functions in the model, which affects its accuracy and precision, but also increases the computational costs associated to the forecasting process. We then proceeded to compare our model to other models in literature. In our comparison, each model was trained and tested by the implementation of a grid search algorithm, a method which tests every possible combination and finds the optimal parameters for the model. We tested the grid size from 1 to 10 for SOLDA T2FTS. For the other models, we tested the number of partitions from 1 to 50, and the order of the models was from 1 to 3. Considering all models, the comparison was performed on the same design approach. All models were trained and tested using the sliding window methodology and ranked according to their RMSE mean values. The models were trained and tested with original and first-order differentiated data, which usually performs better because it makes the time series stationary, or at least closer to stationary. Now let's look at Table 3, the calculated RMSE values. We can see that the T2FTS was ranked at number 1, and although it took longer to execute, 74 seconds, it obtained the lowest RMSE value, 79, in comparison to the other models. So considering these results, our conclusions are that SOLDA can be an efficient tool for defining the number of membership functions in the universe of discourse in fuzzy time series prediction models. And considering the RMSE forecasting values as comparison metrics, SOLDA T2FTS outperformed other advanced models from literature. For future works, we intend to improve SOLDA T2FTS by further exploring the SOLDA algorithm in order to use it not only for data partitioning but also to define the shape of fuzzy membership functions. The authors would like to thank the support of CAPES, FAPEMIG, CNPq, and the Federal University of Juiz de Fora for the technical and financial support. I also leave here our contact information. Thank you all.